Hi everybody. Now that we know how to represent graphs with data structures in order to make computations, we can start answering questions about the properties of the graphs. For instance, a very important question in many problems, in many practical situations, is whether the graph is connected or not, meaning whether all the vertices can be reached from the other vertices. Okay, this is important, for instance, when we have a graph that is the representation of, for instance, a computer network. Okay, so we would like that every computer in the network can talk to each other. Okay, so we would like the graph to be connected. This is also important, for instance, when we are designing the communications network in a country. We would like to be able to reach every city in the country from any other city, okay, or any street in a city from any other street. Okay, so we would like the graph to be connected. And this is something that we can now easily solve. We can check for connectivity with the representation that we studied in the previous lecture, the adjacency matrix. Okay, so let's introduce a few concepts, and then we will see how to use the adjacency matrix in order to check whether a graph is connected or not. So the first definition that we need is what we call reachability. Okay, so we are going to say that um, a vertex is reachable from another vertex if there exists a path from the original vertex into the other one. Okay, so V is reachable from U if there is a path that goes from U to B. Okay, this is a very natural definition, because what is reachable from some place is any other vertex that I can go to with a path. Okay, this is something that we have already used in the previous units, in units 1 and 2, for instance, when we were minimizing finite automata, deterministic finite automata. The first thing that we did was to find whether all the states in the automaton were reachable from the initial state, and we removed all the states that were not reachable. Okay, so this is exactly this definition. States that are reachable from the initial state are those that we can get to from the initial state with a path. Also, in unit 2, when we were eliminating useless symbols in formal grammars, we were looking for symbols that were not reachable. Okay, not reachable um, from the axiom of the grammar, from the initial variable of the grammar. And in that case, the situation is exactly the same. If we think of the variables as nodes in a graph, and we think about the derivations, the different productions in the grammar as connections between the different variables, as edges between the different variables, then those variables that we can reach from the initial variable, from the axiom, are exactly those for which there exists a path from the axiom to the variable. Okay, so this is a very natural definition. Reachability in graphs reflects the idea of being able to get from a vertex to another vertex. Okay, and this reachability property has some some interesting properties related to how we can see this as an equivalence relation. So for instance, we see that there is always a trivial path of length 0. Remember that we consider a vertex as a path of length 0, so any vertex is reachable from itself. So this relationship is reflexive. Every vertex is reachable from itself. The relationship is reflexive. Okay. Also, if we have a path from a vertex U to a vertex B, and then a path from the vertex B to another vertex W, then we can concatenate the two paths to form a path from U to W. Okay? So in this case, what we have is that the relationship is transitive. Okay? If we can go from U to B, we can go from B to W, then we can go from U to W, and that is exactly the definition of being transitive. Okay. Also, if the graph is not directed, then when we have a path from U to V, we also have a path from V to U, because all the edges go in both directions. Okay, so in this case, the relationship is also symmetric. And when we have then an undirected graph, we have a relationship, what vertices are reachable from other vertices, that is reflexive, transitive, and symmetric, and that this is the definition of an equivalence relation. It's not important to remember all these details about what is an equivalence relation and all that you may have studied in algebra, for instance, but it is important to notice that every vertex is reachable from itself, that if we can go from U to V and V to W, then we can go from U to W, and that in non-directed graphs we have this symmetry property. If we can go from U to V, we can go from V to G. Okay? With this idea of reachability, we can also define what we call the connected components of a graph. This idea is very simple, okay? But the mathematical definition may be a bit more complicated. So let me give you first an example, and then we go back to the definition. So imagine, for instance, that we have a graph, a very simple graph, like this one here. We have these vertices with these connections. Okay, you may remember this example. This is an example that we have been using when we were talking about non-directed graphs. Okay, so here you can see that if we are in this vertex, we can reach these other two vertices. Okay, if we are here in this vertex, this was, I think this was vertex 1, vertex 2, vertex 5, vertex 4, 6, and 3. Okay? So from 1, I can reach vertex 2, and I can reach vertex 5. From 3, I can reach vertex 6, and from 4, I cannot reach anything other than 4 itself. Okay? So what we call connected components in this graph are the sets of vertices that are reachable from each other. Okay? So in this case we have 3 connected components, 1 to 5, 3, 6, and 4. Okay? And this is a very, very natural condition, and it's also very important, for instance, in the context of the problems that I was talking about before. For instance, when we have a network of computers, okay, what are the connected components? What are the computers that can talk to each other? Okay, so this is something mathematically defined as the equivalence classes of the equivalence relation of reachability. Okay, so if you remember what is an equivalence relationship and what are the equivalence classes, the elements that are related to each other, then that is a very formal mathematical way of defining connected components. If you don't remember that, a connected component is just the set of vertices that are reachable from each other, and that includes all the vertices that are reachable from the vertex in the connected component. So in the example it was very clear, 1, 2, and 5 were connected to each other, and there were no other vertices that were connected to the vertices in that set. Okay, so that is a connected component. And for a graph to be connected, what we are interested in, for instance, when we have a network of computers, we want it to be connected, what we must have is that there is only one connected component in the graph. Okay, if there is only one connected component in the graph, it means that all the vertices are reachable from the other vertices. Okay, if not, then we have several different connected components, and each of the connected components is a subgraph that is connected. Okay, but the whole graph may be not connected if we have more than one connected component. So what we are interested in is in developing algorithms to test whether the graph is connected or not, and to also find the connected components. Okay, this idea of the connected components applies when we have an equivalence relationship, and for that we need the reachability relationship to be symmetric. So this applies to graphs that are not directed. In the case of graphs that are directed, we have a different notion, what we call strong connectivity. Okay, so now what we want is that all vertices are mutually reachable from each other. Okay, so we want that there are paths from U to B and from B to U. In the case of non-directed graphs, this comes directly from the definition, because all the edges go in both directions. So if we have a path from U to B, we also have a path from B to U. But in directed graphs, this may not be the case. For instance, in the graph that we have in the diagram, we can see that 3 is reachable from 6, but 6 is not reachable from 3. There is no path from 3 to 6. So here we have a different notion, a different concept, what we call strongly connected components. Okay, strongly connected components are sets of vertices that are mutually reachable. So for any pair of vertices in the strongly connected component, U is reachable from B and B is reachable from U. And the strongly connected component includes all the vertices that are reachable, mutually reachable with the vertex in the set, the vertices in the set. Okay, so for instance, in this example here, we have three different connected components. We have 1, 2, 4, and 5. They are mutually reachable. I can go from 1 to 2 to 5 to 4 with a path, and I can go from 4 to 1 to 2 to 5, from 5 to 4 to 1 to 2, and from 1 to the other 3. Okay, so they are mutually reachable. If I want to go from 2 to any of the other 3, I can go with a path, and also for the other vertices. Okay, but in the case of 6 and 3, notice that 6 is in a strongly connected component, because of course 6 is reachable from itself, but 3 is not in the same connected component. okay? Because 3 is reachable from 6, but 6 is not reachable from 3, okay? And we require that the vertices are mutually reachable. I can go from U to V and from V to U, okay? So let me give you an example of a graph that is but would be strongly connected, okay? So for instance, if I have something like this, a graph like this one here, in this case, this graph is strongly connected. Let me give you names to the different vertices, and notice that I can go from 1 to 2, also to 4, and then I can go also to 3, for instance, okay, using, for instance, this path here. If I take 2, I can go to 3, I can go to 1, I can go also to 4. And if you check the other vertices, you can go from 3 to 1 and to 2 and also to 4. From 4 you can go to 3 to 1 and to 2, okay? So all the vertices are mutually reachable, and in this case the graph is strongly connected, okay? So you can have directed graphs with just one strongly connected component, and in that case we say that the graph is strongly connected. Okay, so we have these two different notions of connection in the case of not directed graphs, and of strongly connection in the case of directed graphs. And we would like to know whether, or to have an algorithm to determine whether a given graph is connected if it is not directed, or strongly connected if it is directed, okay? If we have a very small graph and it is not directed, it is very easy to see from the diagram whether it is connected or not, because we clearly can identify the different connected components, okay? But if it is big, let's say if we have millions of nodes, of course it's impossible to do that computation, that determination from the diagram. We cannot take a look at all the different nodes in a very big graph, okay? Also, when we have graphs that are directed, it can be difficult to see whether they are strongly connected or not. For instance, imagine that we have something like this. We have a graph like this. Okay, this graph is not strongly connected, okay? It could look as if it is strongly connected, but in fact from vertex 1 to 1 you can reach all the other vertices. From 1 you can reach of course 1, and then 2, 3, 4 and 5, but for instance from 5 you can only reach 5, okay? So in fact in this case we would have that each vertex is on a component by itself, okay? So 1 is in a component because no other vertex can reach 1. 2 is in another component because from 2 we can reach 3, but from 3 we cannot reach 2. 3 is in another component because from 3 we can only reach itself. And the same happens with 4 and 5. From 5 we cannot reach any other vertex, and from 4 we can reach 5, but from 5 we cannot reach 4, okay? So in this case, even if the diagram looks like connected, in fact this is not connected at all. It's not strongly connected at all, because we have as many strongly connected components as vertices there are in the graph, okay? So we have problems to identify when graphs are connected, for instance, if we have many vertices, or if the graph is directed. Okay, so we would like to have an algorithm that allows us to compute whether the graph is connected or not, or strongly connected or not, without having to resort to the diagram, because it can be difficult or it can be misleading in some cases. Okay, so the idea here is to use the adjacency matrix that we defined in the previous lecture, and from that make some computations in order to find whether the graph is connected or not, or strongly connected or not. For that, we need to first define another concept, another notion that is related to the notion of reachability that we have already defined in this lecture. Okay, remember that we say that a vertex V is reachable from a vertex U if there is a path from U to V. Okay, so now what we are going to make a more fine definition in order of the length of the path that we can use to reach a vertex from another. Okay, so we say that a vertex V is order k reachable, or simply k reachable from another vertex U, if there is a path, but this path has length k, and with this path we can go from U to B. Okay, so if there is a path from U to B, we say that the vertex is reachable, that V is reachable from U, and if this path has length k, then we say that the vertex V is k reachable from U. Okay, so then, as particular cases, we have that a vertex is always reachable from itself with a length path of length 0, so it's always 0 reachable from itself. Okay, of course a vertex is reachable from another if it is reachable, k reachable for some k. Okay, because if it is reachable, it means that there is at least a path, and the length of that path gives us the k reachability. Okay, and of course we can define this k reachability for k0, 1, 2, and more. Okay, so with this definition in mind, we can try to find what we are interested in, that is the reachability matrix. The reachability matrix is similar to the adjacency matrix, in which we had a 1 in position ij if there was an edge from vertex I to vertex j. Okay, that was the definition that we worked with in the previous lecture. And now we are interested in not only whether vertices are reachable with only an edge, but also in whether vertices are reachable with paths of some length. Okay, so this is the matrix that we defined here, in which we have a 1 in position ij if there is a path from I to j, from vertex in position I to vertex in position j. Or to put it in another way, if vj is reachable from vi. Okay, because this means that there is a path from vi to j. Again, this is a n times n Boolean matrix in which we have n rows, n columns, n is the number of vertices, and we have zeros and ones. And the ones will mean that we can go from vertex in position I to the vertex in position j. Okay, so why is this matrix important to us? This matrix is important to us because if this matrix has no zeros, then it means that the graph is connected or strongly connected in the case of directed graphs. This is clear because in a connected or strongly connected graph, every vertex is reachable from each other, okay? So in this reachability matrix, all the positions must be 1. If there is a 0, it means that there is a vertex that is not reachable from another vertex, and then the graph is not connected. So we can have no zeros. So we would like to compute this matrix, okay? We would like to be able to have this matrix and then check if there is any 0 in the matrix, and then we can solve the question of whether the graph is connected or not. And in order to do that, we are going to use some auxiliary matrices. The auxiliary matrices that we are going to use are the matrices for the k-reachability relationship. Okay, so we are going to define matrices for the k-reachability relationships in a similar way to the definition of the reachability matrix. So notice that the only difference here is that now we impose the condition that the path that connects vi with bj is of length k. So we define an n times n Boolean matrix, again, in which we have ones in the positions ij, where j is reachable from I with a path of length k. So it's similar to the reachability matrix, but now we impose that the paths connecting the vertices cannot be of any possible length, but only of length k. So if we knew all these matrices for k equals 0, k equal 1, k equal 2, k equal 3, then, and so on, up to infinity, we could compute the reachability matrix. Because for path to exist, there must be a path of some length. Okay, that path must have some length, and then there must be a 1 in the corresponding reachability, k-reachability matrix. Okay, so if we would be, if we were able to compute these matrices, we would be closer to having the reachability matrix and to answer the question of whether the graph is connected or not. Okay, so, well, this seems to have made our problem infinitely more complicated. We were trying to solve the question of whether the graph is connected or not. That is a yes-no question. It is either connected or not. This is just one bit of information, 0 or 1, 0 for not connected, 1 for connected. Then we extended the problem to finding the reachability matrix, in which we have n squared bits, meaning each one whether a pair of vertices is connected or not. Okay, so maybe it seems that the problem is more complicated. But now we have an infinite number of matrices, each with n squared bits. Okay, so to determine one bit, it seems that we need to compute an infinite number of bits. So this may seem like a dead end. It may seem that we cannot solve the problem in this way. But fortunately, there is a relationship of these k-order reachability matrices with something that we already know how to compute. Okay? Because notice that when we talk about the adjacency matrix, we have exactly M1, the one reachability matrix, because the adjacency matrix has a 1 whenever there is an edge between vertex I and vertex j. But an edge is exactly a path of length 1. So the adjacency matrix has a 1 in position I j if there is a path of length 1 from vertex I to vertex j, and that is exactly the definition of the one reachability matrix. So at least we know how to compute one of these matrices. Also notice that M0, the zero reachability matrix, is the identity matrix, is the matrix that has ones in the diagonal and it's zero everywhere else, okay? Because the only vertices that are reachable with paths of length zero are the vertices themselves, okay? So a vertex is reachable from itself with a path of length 0, and you cannot reach any other vertex with a path of length 0. So the zero reachability matrix is the identity matrix, ones on the diagonal and 0 everywhere else. And well, let's see how we could compute the next matrix. We know how to compute the zero reachability matrix. We know how to compute the one reachability matrix because it's the adjacency matrix. What about the two reachability matrix? The matrix that gives us ones in the positions where there are paths of length 2. So, well, for instance, imagine that we are trying to compute the two reachability matrix for this graph in the diagram, and we can see that, well, for instance, from 1 to 2 I can follow this arrow and then this arrow, okay? So I can go from 1 to 2 with a path of length 2. So I can write a 1 in position 1, 2, because I can go from 1 to 2 with an arrow, with a path of length 2, okay? Notice also that I can go from 1 to 4 with a path of length 2. I can go first to 2 and then to 4, and I have a path of length 2. Also, I can go from 1 to 2 and then to 5, and then I have a path of length 2 from 1 to 5. So this gives us the one in position 1, 5, and we also had this one in position 1, 4, because we can go from 1 to 2 and then to 4, okay? And following this procedure with an enumeration of all the paths of length 2, we can easily, or well, not so easily, but we can fill in all these matrices here. For instance, for this position, notice that I can go from 2 to 4 and then to 1. For this position, notice that I can go from 2 to 2 and then again to 2 to use I can use the loop twice. For instance, for this position here, I can go from 5 to 4 and then back to 5 and so on, okay? So, well, if you have patience, you can fill in this matrix, which is the two reachability matrix, with all the paths of length 2. Also, you can do the same for length 3, length 4, and so on, but it gets complicated, it gets boring, and if you have many different vertices, this is time consuming and is prone to errors. You can forget some path in the process. So the question is whether we can compute these matrices in a simpler way. And the answer is that yes, we can do that, and in fact we can do it with something that we already know how to do, and this is matrix multiplication. So if we want to find the k reachability matrix, we can find it from the kth power of the adjacency matrix, okay? And this is clear, for instance, for m0 because this is m to the power 0, which is the identity matrix, and we already know that the zero reachability matrix is the identity matrix. Of course, m1 is m to the power 1 because we have already said that the one reachability matrix is the adjacency matrix. Okay, and for instance, we can compute the two reachability matrix as the square of the adjacency matrix. Why is that so? Let me give you an example, and you will see that we can do this in general. Okay, so let's draw a very simple example. Imagine that we have this graph here, 1, 2, and 3, and the adjacency matrix of this graph is 0, 1, 0 because we have an edge from 1 to 2, 0, 0, 1 because we have an edge from 2 to 3, and 0, 0, 0. Okay, because from 3 there are no edges coming out. Okay, and of course the two reachability matrix in this graph is just 0, 0, 1 because we have this path of length 2 from 1 to 3, and the other elements of the matrix must be 0 because there are no other paths of length 2. Okay, so let's compute m squared. M squared is going to be this matrix multiplied by itself, and let's see what happens. Okay, so notice that for this element here, we need to multiply the first row with the first column of the second matrix, okay? And we compute 0 times 0 plus 1 times 0 plus 0 times 0, okay? Of course, this is 0, but what are we doing here? What we are doing is trying to combine the edge that could be here from 1 to 1 with the edge that could be here from 1 to 1. Okay, so if we had a loop here, if we had something like that, then we would have a 1 in those positions, and then this multiplication will give us 1. Okay, because we would be combining loops of in the vertex 1, and that is a combination of two loops will give us a path of length 1 of length 2 from 1 to 1. Okay, something similar happens if we had a 1 here. Imagine that we had a 1 in this position. This position is for the edge from 2 to 1. We have no edge from 2 to 1 in this graph, but imagine that we had 1. Then in that situation, here in this position, there would be a 1. And when we make the multiplication, here we would have a 1, and this would give us 1. Okay? Why? Because we would be combining an edge that goes from 2 to 1 with from 1 to 2 with an edge that goes back from 2 to 1. Okay, this edge here. So we are combining edges that end in a intermediate position and then go from that intermediate position back to 1. Okay, that is what we are computing when we are doing this multiplication. Let's see an example now with the multiplication for the second element. The second element here, we know that this element is 0, we have just computed that. The second element here comes from multiplying this, multiplying this. Now let me compute, I wanted to compute the third element. This element is also zero, so I wanted to compute this one. So this element comes from multiplying the first row with the third column in the matrix. Okay, so now what we are doing is 0 times 0. We are trying to combine an edge from 1 to 1, which would be this position, with an edge from 1 to 3. That would give us a path of length 2 from 1 to 3. Okay, but there is no that possibility. The second possibility is to multiply this one here with this one here. Now we have an edge from 1 to 2 together with an edge from 2 to 3. And this gives us a path from of length 2 from 1 to 3. So whenever we have two ones simultaneously in the multiplication, it means that we go from 1 to an intermediate vertex, and then from that intermediate vertex to the final destination. Okay, so that's why when we compute the square of the matrix, we obtain paths of length 2. And when we compute other powers of the matrix, what we obtain are paths of increasing length. For instance, if we multiply m2 times m1, we know that this is m squared times m1, which is m to the cube. We are multiplying paths of length 2 with paths of length 1. So we are getting paths of length 3. When we multiply m3 times m1, we are obtaining paths of length 3 combined with paths of length 1. So we obtain in total paths of length 4. Okay, that's why we can obtain with this multiplication m4. Okay, so it turns out that we can obtain all these matrices of the k-reachability relationships just from the adjacency matrix with this computation, with this multiplication. Okay, notice that this multiplication is a Boolean multiplication. Okay, and then if we multiply, for instance, and obtain instead of 0 or 1, we obtain in one of the elements 3 or 4 or 27, then we must replace that number with 1. What we are interested in is whether there exists at least one path of that length, and not the total number of paths. That is what we would obtain if we computed the multiplication in the usual way. Okay, so we compute the multiplication and then we transform any number that we obtain that is greater than 1 into 1, because we want Boolean matrices. Okay, but with this procedure we can obtain the reachability matrix for any k that we want. Okay, but we still have one problem, that it seems that we need to compute all this infinite number of matrices in order to obtain the reachability matrix. Okay, but that is not so. That is not so because, as we can see in the last theorem of this lecture, is that if the graph has n vertices and we want to compute the reachability matrix, that is the matrix that gives us whether there is at least one path between a pair of vertices or not, we don't need to compute all the reachability matrices. We only need to go up to the nth minus 1 matrix, or the nth minus 1 power of the adjacency matrix. Why? Because imagine that we have a path of length greater than n. Since the path, the length of the path is the number of edges, then imagine that we have a graph of 3 vertices, and we have a path of length 3. Then we use one edge, we use another edge, and when we try to use the third edge, we are going to repeat one of the vertices, okay? So if in a graph of n vertices, we have at least n edges in a path, then one of the vertices is going to be repeated, and we can eliminate that part, okay? We can make the same path with without the repetition. For instance, this path starts in 1 and goes to 2, but we can do the same without the repetition here, without the cycle there, okay? So if we have a path of length n or more, we have another path that starts and ends in the same vertices, but with less than n edges in the path, with length less than n, with length at most n minus 1. Okay, so that's why we can go up only to the matrix of reachability of order n minus 1. Okay, so with this we can compute the reachability matrix of a given graph, and then we can compute whether the graph is connected or not. Okay, so this is the procedure that we must follow. We first determine the adjacency matrix, and then we compute the different powers of the matrix up to the power n minus 1, where n is the number of vertices, and then we compute the addition of those matrices, always Boolean addition, okay, so 1 plus 1 is 1 and not 2. So we reduce numbers greater than 1 to 1, and what we obtain is the reachability matrix. And if the reachability matrix is composed only by ones, if there are no zeros, then we know whether the matrix is the graph is connected or not. Okay, so that's what we need to do. This is something that we can do with the computer if the graph is very big, has a lot of vertices, and we can do this with the usual algorithms for matrix multiplications. We can do it also in a more quick way that I will show you in a future video, but if you just want to have an algorithm to compute whether the graph is connected or not, this makes the trick. Okay, so as an exercise, I want you to compute the reachability matrix for the graph that I'm going to draw here now. Okay, so let's consider a graph with 4 vertices, 1, 2, 3, and 4, and imagine that we have connections like these ones here. Okay, I want you to compute the adjacency matrix M1 or M, and then M2, M3, of course M0 is the identity matrix, and then I want you to compute the addition of all these matrices to get the reachability matrix. Okay, and I will give you the solution in a future video. Thank you for listening, and as always, if you have any question or doubt, please use the discussion forum or reach me by email. Goodbye.